what's there in this demo? So you can see that there are two sides. There's where my cursor is. This is the left side of the application, and this is the time domain. So you can see here is milliseconds, all of them. So these 4 panels show 4 different waveforms. And basically, we will describe exactly which one is. First is the input signal. So suppose it's a sine wave here, right? A sinusoidal, so a sine in this case. And when I load the application, it comes with a preloaded, predefined frequency. Here is 100 Hertz. So of course, I can change this frequency up. So I'm making it turn faster. Remember this exponential turning in the unit circle, right? So turning faster, faster, faster. Now I go the other way around, turning slower, slower, slower. The frequency appears here, and I can play actually the signal, right? So it goes to 0, and 0 you basically see a line because it's a DC. So let's continue, stay at, for instance, here 300 Hertz. 400 Hertz almost. So actually, I can actually type the values. If I want 300 Hertz, I just press and go here, update. Then it goes to 300 Hertz. So this is the first top panel. The second panel is my sampling signal. So it's basically representing this train of pulses with a given sampling frequency. So what's the sampling frequency there? It preloads with 48 kilohertz. So it's pretty high. So I can obviously, to see effects of sampling, critical sampling, etc., I will go down. And you see that this has a bit more discretized. I mean, you can put continuous values, but sometimes it goes closer to certain values because just a linear scale with so many values makes it harder. So here again, look at this second panel. The first obviously doesn't change because my input signal is still at 300 Hertz. Now I'm changing the frequency, sampling frequency. So basically the lower the sampling frequency here, going to the left with the slider, basically the spacing, the sampling period increases, right? And the spacing of this train of pulses increases. Means I'm taking less samples per period. And actually this is exactly the third panel here on the left. This is basically a pulse amplitude modulation. So you have this train of pulses here, so pulse, being whose frequency is given by the sampling frequency, right? The period here is diverse. And the amplitudes are all 1. So what you see on the third panel here is basically this initially equal amplitude train of pulses with this new amplitude being modulated by the signal I'm acquiring, so the input signal. So in this case is this 300 Hertz. So if you see here, this is the first period, this is the second period, that's part of the third period. And you can see that for 3000, here 6000 Hertz sampling frequency, and at 300 I will get 20 different samples in one period. So obviously, again, as the more I reduce the sampling frequency, the less samples I get per period, right? And then here in this application we made, the smallest sampling frequency we can add is 3000. So when I'm 3000, how many I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 6000 I have 20, 12,000 I have 40, etc., etc. So it's basically very easy to tell how many I have. So what do we see there? Again, input signal here on the left top panel, sampling signal, the train of pulses, second panel below the first. Third panel is the result of this sampling in the time domain. So again, left is time domain. So I see basically this same train of pulses with the amplitudes now modulated by the original signal. So of course now if I increase the original signal, you will see that these amplitudes here will change, and I will have less and less, obviously increasing the input signal. It's similar effect as decreasing, keeping the input signal constant frequency and decreasing the sampling frequency. I have less samples per period. So on the fourth panel here is the reconstructed signal. So what's going on here is I have a signal, it's entered this system, that's the sampling system with this characteristic. This is the output in the time domain. From this output, I reconstruct a signal that appears on the fourth panel, the bottom one on the left. So this reconstructed signal here, because my sampling rate, sampling frequency is 3000 Hertz, and my fundamental frequency is 800 Hertz, so less than half of the sampling rate, I get the same signal back in the output. So far so good, right? So we are inputting a signal, making an operation on the signal, transforming, taking samples of the signal, so from continuous to discrete, and then we are moving back to continuous. So that's the left side, that's the time domain. We will come back to this and see a bunch of different functions we can play, a bunch of different examples of sampling. Now let's move to the right side. So the right side is this, again, 4 panels, and these 4 panels actually are one-to-one correspondences to the left panels. So the input signal here, the top left, what you see on the right is basically the frequency content of this input signal. So here is time domain, here is frequency domain, right? So you see the spectrum, and basically this is a sine wave, a sinusoidal, and basically it's only one frequency. That's exactly what we discussed in class number 1. First class and class number 2 is the idea of the simplest kind of oscillation. It's just this exponential turning, right, in the unit circle. So basically you have something turning at a constant speed, and basically this speed is the inverse of the frequency, basically the period, right, inverse of the frequency over time. And basically it's related to what you see here is this 863.53 Hertz. It's one component only. Okay. So another I didn't mention, but there is actually some other properties here. You can zoom to better see the frequencies, but also the amplitudes, right? I can zoom the time to see more details. I can also zoom the amplitude if I need. So this is not doing anything, it's just a display. The signal stays the same, it doesn't change the amplitude of the signal, it doesn't change the frequency of the signal, it's just the display of the signal that changes. So I increased here so that you see better, you see a bit better here, and this is the 853 Hertz there. Right. So if I increase, what will happen here? This guy gets closer together, right? More periods, right? Because obviously the period gets smaller, and my frequency goes up. If I decrease, my frequency goes down to 0, and of course I have less period. So again, left and right are basically the same signal, but with different signal representations, as we mentioned in class number 1. So the left side, time domain, right side, frequency domain. Similar to the second graph. So if you look at the second panel there, the one below, in the time domain it was the train of pulses, with again the inverse of the sampling frequencies, the spacing between the pulses. So the frequency component of this train of pulses, the time domain, actually is another train of pulses, but this time in the frequency domain. And these pulses in the frequency domain are in multiples at 0 and in multiples of the sampling frequency. So this is what you see here. So this sampling frequency here, in this case, is 3000 Hertz. So there is one component of this time domain signal, frequency domain at 0, one component at 3000, so Fs, one component at twice 3000, 2Fs, so 6000, 9000, 12,000, 15,000, and this goes forever. And don't forget what we see here, and we decided to present this as just the real part of the frequency domain. Remember that a cosine, because of the Euler's formula, right? You can present the cosine as the sum of these two complex exponentials turning in different directions, right? So plus and minus j, theta. Remember that. So basically, a cosine actually is composed of two signals, the signal and the complex conjugate. So basically, we have a negative and a positive component for a simple harmonic motion. In this case, we are just showing the positive sign, right? So this you will see, you will basically see both options. There are programs that show just the real part, and others shows the complex representation of the signals, right? So basically we saw the first one is the input signal and right part is frequency content. The second one is the sampling signal and right side is frequency component. The third side, what we have is basically the result in the left of the time domain multiplication of this train of pulses and the input signal, and in the right side we have the frequency result of what's happening. So it's hard to tell here. There's some codes, color codes you can see. So you can see something dark here. This gray region actually is basically half of the sampling frequency, right? So if it's 3000 hertz here, basically this is 1500 hertz, right? So you will see if I increase this gray region increases too, right? So again, if it's 8000 hertz here, you will see it to be exactly at 4000 hertz, right? Exactly. So this is just automatically once I put. So of course, since I did it, you see that this I went from 3000 to 8000 hertz on the sampling frequency. Of course, my spacing here got closer together, so my period reduced, my frequency increased. And actually now this component, the frequency component, will be Fs now is 8, 2Fs is 16. Right? If I reduce the zoom here, I will see more of them. Right? So 0, 8000, 16,000, 24,000. I can go the next one will be 32,000, right? Etc. So this I'm just playing here. But what happened is by increasing this, of course, these guys get further apart. Right? If I reduce the sampling frequency, they get closer together. If I increase, they get further apart. So this is the second, that was easy. The third one, so on the left side we saw it's the result of this multiplication, right? Train of pulses and input signal. On the left side, this is crucial, is exactly the consequence of sampling in the frequency domain. And what you see here is that because the representation of this signal here, the train of pulses is another train of pulses with multiples at 0 and multiples of the sampling frequency, this multiplication at the left causes the appearance of these images of the signal. So the signal here is, let me make it at 800 hertz. Make it simpler. So this signal at 800 hertz here will appear around every single one of these pulses in the frequency domain. And don't forget, the positive side, but also in the negative side, we are not showing here. So now we start wondering, right? I mean, what happens when these guys appear? So let me go back to 8000. So far, this is the region of interest, half the sampling rate. This is what I get. So I have this signal here, the 800 hertz, that was my initial signal. It's in the region. These guys, these are all possible aliases, so all frequencies that are created because of the component here of the signal. So don't forget, this is not a component, it's just the result of the characteristics of this sampling signal. These are components that appear. So to show that, let me go to 0 in my frequency. You will see that these guys will disappear. Right? I just have the result of component, frequency component of this guy. Right? So slowly here, they appear and they disappear. Right? Of course, I'm multiplying this by 0. I just have this, what would be this guy, so actually I don't have anything, right? 0. So continuing there, let's go back to 800 just to have it clear. This is the formula that we saw in class number 3. Basically, when you sample, you get all these apparent frequencies at plus or minus n from 0 to an integer to infinite, Fs, so sampling frequency, it's NFS plus or minus the original input frequency. Right? So n equals 0, you have just plus or minus the original. I mean, here I'm just showing plus. Then you have n equals 1, you have Fs plus the original minus the original, 2Fs plus the original, minus the original, 3fs plus, minus, etc. So here it's not a problem. My sampling rate is way bigger than the maximum signal, signal frequency input. And when I reconstruct, I will basically ideally use a brick wall filter, so a filter that actually would have exactly the shape here. Nothing happens in the region where it should be no alias, so until half of the sampling frequency, and then everything is filtered beyond. So this rectangular shape. So basically what you see then, the last panel here, the bottom one, on the left side is the reconstructed signal, so again time domain. On the right side here, you see the frequency component. And you see that this shape actually is not as nice as the top shape, because actually we are calculating the shape. And when you calculate in practice, you have to filter, you have to do a lot of operations. And basically, it's not going to be ideal as the theory just say, okay, of course, if you have this, you have exactly that. There's some artifacts here from the types of windows you do, the types of calculations you do, etc. Right? So this we will not see. This is actually the details about this process you will see in further classes in the MST minor. Here, just assume that this is the representation, but of course, in practice, you get some extra artifacts that's not so beautiful as theoretically you just get one line. Right? Again, it's not that you're adding frequency, it's just the way this is calculated. So in practice, there's some details there. So far so good. Sampling rate is high enough, frequency is. So now let's go up in frequency, right? But we will see, obviously, this guy will start getting closer together, more and more periods for the same zoom. This guy starts going to the right. These guys here start spacing out, so this doesn't change if I change the sampling frequency. These guys, because the input signal I'm going to increase, this will go further to the right, this will go further to the left, this will come to the right, this will come to the left, this will go to the, and etc. etc. So let's go to 3.5, so below half. What you see is that, okay, as expected, right, there's less samples per period, right? Almost more than 2. Basically, here's the signal. I still get my signal at the input, the output. Right? And basically, you see that these images that appear because of the multiplication in the time domain, actually, they are still out of my region of interest. They are still beyond half the sampling rate. So, of course, what happens when I come very close? So let's go to 3,900. So I'm very, very close. So you see they're almost touching, right? So theoretically, no problem. I'm still getting, you see that the reconstruction is kind of getting there. But actually, I can actually go back to exactly this frequency. So this you will see later, it's the details here. But theoretically, there's no problem. I'm very, very close. Practice might be a bit different. So that's why you don't want to go very close, right? And actually the worst is when you come here and do exactly, let's see, 90, and then I'll go to 4,000, exactly half. So what's happening here, so forget this part, let's look here, this is almost at sampling divided by 2, and actually they almost touch. So now let's go here slowly, slowly, until I arrive at exactly 4,000. Looks 97, 98, 99, 4,000. So what happened there? I basically don't have anything at the output because I'm taking exactly 2 samples per period. And because it's a sine wave and because my pulse starts at 0 here, I take one sample exactly when the sine is 0. And the second sample I take exactly at the sine is 0, etc., etc. So in this case, critical sampling that you should not attempt to do because it's always better to have a certain leeway there to avoid exactly this kind of artifacts. But in critical sampling, the question is it possible to sample theoretically a signal exactly at half of the sampling frequency? And the answer is depends. Right? It it is possible, but then it will depend on the phase of the signal. In this case here, you see, because we are using a sine wave or a cosine advanced by a delayed, by pi divided by 2, delayed by 90 degrees. The samples I take, it's obvious, right? If I'm using twice, I'm taking 2 samples per period, are exactly at 0, so I cannot tell whether this was a signal or not. Now let's move the phase here and add a phase delay, a phase advancing, so I'm moving to the left here, this signal. And let's add 90 degrees, and basically I'll have a cosine, and see what happens at the output. There's a signal coming. So what's the best option here? When I arrive at 90, you see, phase here, where my cursor is. Exactly at 90. So when I'm at 90, then I continue to get 2 pulses per period, but I get at the maximum of the signal. So basically, I can reconstruct my signal exactly. And you see that going there, I could still reconstruct that frequency, but basically, it was a signal that was, I don't get the right amplitude. And of course, the worst is the phase at 0, or obviously at 180 degrees, pi. Right, to be exactly the same, I will be taking these samples exactly at the 0 points again. Right. So this is the first very useful example we can see with this, this application we made there, is that yes, it's possible to do critical sampling, but basically you will may not get the output the way you expect. Right? You may not get the right signal. Either you don't get any signal or you may lose the amplitude. So let's go back here to the 0 phase. What happens now if I increase the frequency? I keep my sampling rate at 8,000 and I increase my frequency. So basically this guy here will leave this gray region that was actually exactly where it is now, is half the sampling frequency, and will continue. Right? So that's okay. My input signal is continue. My sampling is not enough to sample. So basically what will happen is that this black guy that's together with the purple guy here, the black guy will continue here on the left, on the right, going more to the right. But then this guy here, that's my sampling frequency, minus this guy, the input signal, because the input signal is increasing, this guy will continue now to the left and will enter my region of interest. And that's exactly the effect of aliasing. So let me go a bit here to, let's say, 4,500. Okay, almost there, 600. Right here, 4,500. So what you see here now is that my original signal is 4,500. This is 4,000 is half the sampling that's now at 8. So what I get at the output is a 3,500 signal, right? So you see that the input signal has a higher frequency than the output signal here. And that's exactly because what I'm filtering, suppose I'm filtering a recall filter, I'm taking everything that's beyond half the sampling rate, I only see this component. And this component actually is an alias of the original signal. It's not anymore the original signal. The original signal is filtered. I don't see the black anymore here. I will see purple here. And of course, if I continue increasing my frequency, this purple will go closer to 0, right? And I'll stop here. Let's say that's right, 6,000 is to have multiple. So when I sample a 6,000 Hertz signal with an 8,000 Hertz sampling frequency at the output, what do I have? This signal here, the input signal disappears, and I have an alias of the first here, image that appears at 2,000 Hertz. So if I sample a 6,000 Hertz with an 8,000 sampling frequency, at the end I get a 2,000 Hertz signal. Right? So I will hear at 2,000 Hertz, and that's basically what you get. So sorry for the high pitch on the original 6,000. And now the reconstructed will be 2,000. Right? So that's the problem with aliasing. Means if you don't know that your original signal was 6,000 and you just see the output, you can't tell whether the original was actually 2,000 or actually was 6,000, or it could be actually a much higher frequency. Let's continue seeing here. Let's continue to increase the input and keep the sampling rate constant. What will happen? If I increase my input frequency here, this first alias will continue to go down until where? Well, what happens when this signal here is 8,000 hertz? So I'll go slow here so that you can see. When it arrives at 8,000 hertz, basically, I will be taking one sample per period. Write it here to be sure. I'm basically taking one sample per period, and my output is 0, because basically all the samples are at the same point, and I have a DC value. So again, if I sample a signal with exactly the same frequency of the signal, and it's exactly the same to the sampling frequency, basically I get 0. So look again, I'll go back to this, but look again, going back to 0 here, my input signal. So what happens is my sampling rate is constant, and I'm increasing the input signal. The output increases proportionally. When it arrives at half the sampling, basically it might or not be sampled, might be 0 or not. When I continue past half the sampling rate, it starts going back, because it's not anymore the original signal, it's the sample coming. Until it continues to slow down, right, to reduce the frequency, I'm increasing my input, but my output is decreasing until it arrives at 0. When it arrives at 0, click here. What you have is if I continue to increase my input, I cannot change the sample rate. It starts increasing the frequency again, right? So you see that now this alias there, the purple alias, is increasing. What will happen when it arrives at 3 times half of the sampling rate, so 12,000 hertz? Basically, it's again critical sampling, but not the original signal anymore, the equivalent without the critical sampling. But basically, it's this alias that is leaving the region of interest here, and a new alias, the alias of this guy here, 2fs minus my original signal. So here is 16,000, right? 2 times 8,000 minus 12,000 here. It's actually 12,000. So this now, 16 minus 12 is basically 4. So that's the green you see here. And again, it continues then to go down the frequency. My input is increasing, and my result is decreasing. But it's the second image here now that we are measuring. Not anymore. Even this is already up. And it continues. When it reaches exactly 16, what happens? Sorry. It goes to 0 again. When it passes 16, here, it starts increasing again. And you see that this is continuing forever. Right? So if I increase my signal, it goes up to half the sampling frequency, and that's fine. If it passes sampling frequency, it will be aliased back until it reaches 0, reducing the frequency, while my input is increasing always. Once it reaches 0, it starts increasing again. Once it reaches half the sampling rate, it starts decreasing again, etc. So you keep turning, changing directions, going to 0, accelerating, changing directions, going to 0, accelerating, changing directions, etc. That's exactly the graph we showed in class. That's very important to understand, right? So you saw this here in practice, and basically is these images of these multiples of sampling frequency that are coming back into the region of interest, right? So if I don't want aliasing to happen, I have to add a filter here, and let's just put one filter that we can explain which filter. I'm changing the order. I mean, I'm making the filter more or less abrupt, very abrupt filter here. And you will see that once I arrive at 4,000 hertz, so far so good. Once I pass 4,000, there's no more signal. Even if you see on the third panel here on the right, the alias is there, but because I'm low-pass filtering this signal, there's nothing else. Right? So this is a mathematical representation, but actually there is nothing at the output because I'm using an anti-aliasing filter. If I take this anti-aliasing filter, what I will see is the alias here. Right. So that's I think it's a very good example of how, I mean, and again, this is an application, right? How sampling works, and this is an application that's available. It's still beta, right? I mean, it's just under development. But basically, you can play with values, and of course, then make things more interesting. You can have signals that have more than only one harmonic, right? For instance, you can have here 4,000 hertz, 400 hertz signal, and say, but I want 2 harmonics. So it's 400 and 800. I want 3, 400, 800, 1,200, etc. And then you start seeing the effect of aliasing in more complex signals, right? What will happen here if I add 10, or now this is the maximum I can add. The last harmonic here is exactly at half the sampling rate, right? So of course, if I increase slightly here, even a few hertz, what will happen is it will start having some aliasing from the very high frequency image to the this guy here in the first sampling rate, 1 time fs, right? So you see obviously that the effect of aliasing is the same if I have one signal or complex, simple signal, simple harmonic motion, or a complex signal, right? As long as any of the frequencies go over half the sampling rate, multiples, these frequencies will be created in images of the sampling rate here, and will be moving back to the audible range, right, or into the range of interest in this case. You see all these different colors here. Another one. All the different images that were created because of sampling. See, from the 2fs here, from the fs here, etc. So you see how noisy and distorted my signal becomes. So this is my original. That is a complex signal. Of course, I'm having a lot of partials here, or harmonics. Actually, there are multiples, but these will sound very different, right? And this, I mean, the frequency is different, but also the fundamental perceived is, but also it's a distortion because they are not necessarily multiples anymore. Right? These should sound a bit better because they are multiples. These are not necessarily multiples. These two numbers don't have any multiple relationship. So I'll stop here, but we will do another one. Then talking about quantization, changing here the bit depth. So I'm using 16 bits here. What happens if I go very low on the number of bits that I'm quantizing the signal, and actually adding some jitter here to reduce this effect of quantization. So let's stop here. And that's a demo showing this interface. Again, you can play here at home with different parameters and see what happens. Bug reports are welcome. So if you see something that sounds wrong there, tell us, because this is under development. Thanks again.